Hey guys, and welcome to our second lesson in probability. So today we'll be looking at combinations. And the biggest lesson I want to give you guys for combinations is how they differ from permutations. And that's what we will be dealing with for the first 10 to 20 minutes. And the reason is because it's very important to understand why they're so different, because the way we approach the problems is actually a lot more different. The best way to introduce combinations is to start with some example, and I'll get to it right now. So, let's start. Suppose you start with 5 objects, okay? So we have 5 objects. And those 5 objects are the letters A, B, C, D, and E. Okay, recall in the last video, each of these is an object, right? The letter A is one object, the letter B is one object, and so on. And this is what we're interested in. We are interested in determining the number of different groups of 3 objects that can be formed from the 5 objects that we have. So that can be formed from the 5 objects, which are these objects. And the question is, how many different groups do we have? How many different groups that we have? So how many different groups are there? Okay, so how do we even begin to solve this problem? Well, let's first do it step by step. We're interested in determining the number of different groups of 3 objects that can be formed from the 5 objects. Well, if we learned anything from the last video, we always like to start with spaces, right? How many spaces should we start with? Well, we want groups of 3 objects, okay? 3 objects, which means we should have 1, 2, 3 spaces, right? 3 placeholders for the letters. Not 5, because we're only interested in 3 objects that can form a group. So, experiment number 1 is choosing an object from the 5. Well, how many different objects do I have to choose from in experiment 1? I haven't chosen one yet, so I could choose any of these 5 letters, right? So that means experiment 1 has 5 outcomes. Experiment number 2, well, if I chose a letter, say I chose the letter A in the first slot, I have 4 different letters to choose from. So that's 4 outcomes for experiment 2. And let's say I chose, I don't know, C. Okay, I've chosen A, I've chosen C, so I only have B, D, and E, which is just 3 objects left. So I have 3 objects, or 3 outcomes for experiment number 3. And let's say I chose D. And we stop here, right? Because we can't choose a 4th object because we're only interested in groups of 3. And this gives us 60, well, 60 what? Well, we're choosing a letter here, and a letter here. Oh, 60 permutations, right? That's what we did last video. Permutations. And recall, in a permutation, the order of your objects matters. What does that mean? Well, that just means that ACD is different, so not equal, to ADC, for example. Right? Or it's not equal to CDA, which isn't equal to CAD. Oops, that's D. CAD, which isn't equal to DCA, which is not equal to DAC. Right? So you have 6 different arrangements that are not equal to each other in a permutation. They're not equal to each other in a permutation because the order of your objects are different in each of these arrangements, right? Notice how you have the same objects in all of these, right? A, C, and D. However, we're always rearranging them, and that's why order matters in a permutation. So we have 60 for a permutation. And right now, we get to why a combination is different from a permutation. In a combination, the order of your objects does not matter. Does not matter. So the group ACD is equal to ADC, is equal to CAD, and so on. I'll just write them out right now so we see what's going on. In a combination. In a combination. This, all of these 6 groups are equal in a combination because they contain the same object. Because the order of your objects does not matter in a combination. So even though we rearrange the letters or rearrange the objects within each group, this is the same group in a combination. And the way I like to think about combinations is, think about doing a group project with your friends in class and you're sitting at a table. It's you, your friend Bob, and Mike. Mike, and Bob is the same group as Bob, Mike, and you, right? Even though you guys maybe switch seats, you guys are essentially the same group. You didn't change the group, so you only count your group once. In a permutation, that's not the case. We like to think of them as different arrangements, so we do count these as separate cases. So in a permutation, we do count these as 6 different cases. In a combination, this is just one, because they're all equal. So that must tell you that we should have less combinations than permutations in general, because we're overcounting these groups. So how do we account for that? Well, we still have 5 times 4 times 3, right? Because that's how many different arrangements we could get. But now we have to account for the fact that we have groups that are equal to each other. Well, we have 3 objects to choose from, and the rearrangement of these objects doesn't matter in a combination. So we have to know how many different ways can we rearrange this, and then we divide by that error. Well, how many different ways can you rearrange these 3 letters? Oh, Well, you have 3 times 2 times 1 different ways, right? Because your first lot, you have 3 of the letters to choose from, then 2, and then 1. Oh, but we have to divide by it because in the combination, all of these are equal. So we're dividing out this error. And this becomes 10 different groups or combinations. And that's that. So I'm going to give you guys tips on how to solve these combination problems. And I'll get to a general formula right after, but first I want to give you tips. Because they're still they're not harder than doing permutations, they're just a little trickier. And you'll see why. So, my first tip I can give you is if you have a question that's asking how many different groups or how many different committees or how many different organizations, think combinations, not permutations. So groups in your question essentially means think combinations, not permutations. And these next few tips are actually the same as permutations because first you have to recognize that you're dealing with combinations, and then these next tips follow the same as how you deal with permutations. So the next tip I can give you is, what are your experiments? Okay, we still care about that. What are your experiments? Actually, what are your experiments? The next thing you should be looking out for is how many experiments do you even have? So how many experiments do you have? And then the last tip is, well, how many outcomes does each experiment have? How many outcomes does each experiment have? And why do we care about these last 3 tips? Well, when we looked at our permutations, right, we always looked for the number of experiments and what they were, and then the number of outcomes for each experiment. And the reason why we care about it so much is the basic principle of counting says, if you have a certain number of experiments, and for each experiment you have a certain number of outcomes, the total number of outcomes you can get is you multiply each of the outcomes from each experiment, and that gives you the total number of outcomes. And it still works for combinations, and we'll see an example shortly. But first, I want to give you guys some formulas and some definitions. So, here we go. In general, the total number of different groups, of are objects that can be formed from n objects. So you have a total of n objects. from n objects is the following. So you have this formula, n times n minus 1 times all the way to n minus r plus 1 all over r factorial. So you won't have to know this formula, and because it actually reduces to something very nice. In the numerator you have, so I'll color code this, in the numerator you have n factorial over the difference between r and n, so n minus r, but this is in a factorial, so once you subtract n minus r, you have the factorial, and then you have to multiply by r factorial. And what is that? What is this thing? Well, that's the number of different combinations, the number of different groups. This is the number of different combinations. And now we have a nice way of actually finding out the number of different combinations for problems. So this is very important. You guys have to remember this. And you'll see shortly that we won't have to write this constantly because we'll have a nice notation to cover that. But that is the number of different groups of combinations. And just to translate it back to this problem, well, n objects is our total number of objects. So in this problem, n must be 5, right? Because that's the total number of objects we have. Okay, so n equals 5. Well, that must mean r equals 3, right? Because we're choosing r from the 5 objects. So r equals 3. And to find the number of different groups that can be formed from 5 objects, and we're choosing 3, well, let's do that formula. In the numerator, I should have n factorial. Oh, but n equals 5, so 5 factorial. And then I'm subtracting 5 and 3. So 5 minus 3 is 2. So 5 minus 3 factorial times r factorial. R factorial is 3 factorial. And this is just 2 factorial, right? 5 minus 3 is 2, and then 2 factorial. Okay, well, oops. 5 factorial is just 5 times 4 times 3 times 2 times 1, right? That's what the factorial is. In the numerator, 2 factorial is just 2 times 1. And then times 3 factorial. So times 3 times 2 times 1. And just to show you guys how we can get from here to here, well, I notice I have a 2 times 1 here in the denominator and a 2 times 1 in the numerator. I could cancel those out. And what you end up getting is 5 times 4 times 3 over 3 times 2 times 1, which is exactly what we had here. And that's it, we're done. And notice, just by using this formula, we didn't have to go through the hassle of finding out first how many permutations do we have, and then how many different ways can we rearrange these objects, because in the combination order it doesn't matter. Oh, but this formula tells you how to find the number of different combinations anyway, and we did it here in like less than 10 seconds, rather than doing this. So you see why this formula is so beneficial. Okay, so the biggest takeaway before we move on to problems is in the combination, the order of your objects does not matter, which means that you end up over counting by a certain number. So you have to divide that number out. But it just reduces to this formula. And that's what you have to remember. So next up we'll be doing notation. So we're going to see how we could just write that out nicely and some properties of the combination, which are actually very important. Okay. So let me erase the problem. Make sure you have these tips in your notes, because I'm going to be erasing it right now. You're going to see that these combination problems might be a little more tricky than permutation problems, but they still have the same approach. First, you guys have to recognize that it is a combination problem. But you guys can trust me in this video to just do combination problems. But once we actually do the end of the chapter problems after this video and the next, which is going to be about other stuff. Once we do the chapter 1 problems, which just deals with all the lessons we have done so far, I wouldn't be telling you beforehand if it's a combination problem or a permutation problem. You have to figure that out by yourself. So it's good to get in the habit of actually figuring it out beforehand. So, notation. So let me just rewrite that formula. So you have n factorial over n minus r factorial times r factorial. Notationally, we like to write it like this. N here and r right there. I don't like how that looks. Let me actually color code that. N on top, and on the bottom you have the r. Notice that this is not a fraction. All you have is two open parentheses. On the top you have an n, and on the bottom you have an r. So the way you read that is the following: n choose r. N choose r. Because you're choosing r objects from the n that you have. N choose r is that, and this is that. So whenever you see this, think of this, and whenever you see this, think of that. That's just notation. So, whenever you see this, don't get scared. It just means this. Some textbooks have a different notation. They may use n capital C and then r, which means the same thing. N choose r, and you may also see something like this. N and r are like functions of C. So you're choosing n and you're choosing r for the C. For probability, once we actually deal with probability,
okay,
this
so
ends up being
now we go on to
cleaner
properties
and a lot nicer to deal with.
R.
So I won't
let's
be
get
using
to that.
these two, but if you do see it in your textbook, it just means this. So it's the same thing, but I just like this better, and that's how I learned it. Okay, so now we move on to the properties of n choose r. Okay, so properties of n choose r. Properties, okay. And the first property is, well, r, actually let me put in first property. R has to be between 0 and n, okay? And if r is greater than n, or r is less than 0, then n choose r is just 0. n choose r is 0. And the reason is, well, if r is greater than n, think about that for a second. If r is greater than n, how can you pick 6 objects from 5 to form a group? You can't, because you don't have 6 objects to choose from the beginning. So we only have 0. We have 0 groups because we can't choose 6 objects from 5. You know, you can't have r being greater than n. And r being less than 0, well, you can't choose negative objects, right? That doesn't make any sense. So you only can do it 0 ways. So that's 0. That's our first property. For number 2, first recall from our last video. Wow, I can't spell today. Recall that 0 factorial was 1. So n choose 0, right? In this case, r equals 0. N choose 0 is just n factorial over n minus r, or n minus 0, which is just n, factorial, so n factorial, times r factorial, but r is 0, so you just 0 factorial. 0 factorial is 1, so you just multiply by 1. I could cancel out n factorial, and what you end up getting is 1 over 1, which is just 1, right? Also, n choose n is just, well, n choose n is n factorial over n minus n factorial, times r factorial, but r is n, so n factorial. So you still have n factorial on the top. N minus n is 0. 0 factorial is just 1, so you have a 1 here, times n factorial. Oh, you get the same thing, right? You can cancel out the n factorials. You get 1 over 1, which is just 1. So 2 of these properties just say that n choose 0 is equal to n choose n, which are both equal to 1. Right? Because you only could have one group where you choose, let's say, 5 objects from 5 objects, right? And because if you rearrange those objects, it's the same group. Remember, combination. So you have 1. The only way you could choose 0 objects from n is one way. You don't. That's the one way. That's the one group. So that group it's an empty group. That group doesn't exist, but it is one group, right? Okay. And that basically covers all the properties, I think. So, don't forget these properties. They're very important, especially when we start doing probability. So this is very important, and keep it in the back of your head. And it brings us to our first example that uses this notation. So let's begin. Example. Okay, so a committee. I don't know if I'm spelling committee right. Correct me if I'm wrong. I don't think there are 2 T's, but maybe there are. Anyway, a committee of 4 is to be formed. A committee of 4 is to be formed from a group of 20 people, or from 20 people. How many different committees are there? How many different committees are there? Or when you hear committee, think of a group. So different committees just means how many different groups. So how many different groups or committees, how many different groups are there? So from the tips I gave you guys, first you have to recognize, is this a combination problem or is it not? Well, this gives it away right here. The question is asking how many different groups are there. So you should think combinations and not permutations. Okay. And the next thing you should recognize is, what is your experiment and how many are there? Well, the only experiment I can think of is I'm choosing 4 people from 20 people to form a group. That's the only experiment I have, and that is the experiment. So, experiment number one, is I'm choosing 4 people from 20 people. 4 people from 20 people, right? To form that group with 4 people in it. Okay. And now, well, this is the only experiment we have actually. So we just have one experiment. And for combination problems, you have to recognize what is your N and what is your R. Because if you know both of them, well, guess what? You already solved the problem. Okay, so what is our N? And the way I like to recognize my N is usually by just following the property and not overthinking. Because the N is always greater or equal to R. Well, if it's greater than R, then you're done, right? Because, well, 20 is already greater than 4, so I know my N is 20. And if they were equal, then it doesn't really matter what you choose because they're equal. And it could be 20 or it could equal 20. Another way to find the N is think, well, look at the question. You're choosing 4 people from the 20, the larger pool of people. N choose R. 20 choose 4 people. That's another way you could find your N and your R. And so your R must be 4 then. You've recognized it's a combination problem. You found all the experiments you can, and you understand what your experiment is. For a combination problem, you have to first find your N and your R, and then you have to find the number of outcomes. Well, think about it. You already have your N and you have your R, and then you're done. This is the number of outcomes. Oh, so just N choose R, which is 20 choose 4. 20 choose 4. Which ends up being 4,845 different groups. Okay? Because that's what the question was asking. That's what we found. This is the number of different groups that we can form from the 20 people. And each group contains 4 people. And it ends up being this many. And that's it, we're done for this problem. And of course, you could have done this the longer way, like we did in the first example, by first finding the number of different permutations. So you would have, I don't even want to do it, but just to show you guys, first you would have to choose 4 people, right? So you would have 4 slots, 1, 2, 3, 4. In your first experiment, you would have 20 people to choose from, times the 19 in the next, times 18, and times 17. And this will give you the number of different permutations. But remember, in a combination, order doesn't matter. So it doesn't matter if we rearrange those 4 people within the group, it's the same group. So we have to divide this by, well, we have to divide it by the number of ways you could rearrange 4 people. Oh, that's just 4 factorial, or 4 times 3 times 2 times 1. And if you guys want to try it out, you'll see that this ends up being this, and they're both equal. This is way faster, and I encourage you guys to stick to this because, especially in probabilities, this will be a nice way of representing the total number of outcomes and so on. And we are done. And it brings us to our next example, which I'll do here. Okay. This is a two-part example. The first part isn't so bad. The second part, it has two solutions, and it may have more, but I'll just present you two solutions. So don't worry about part B yet, but part A goes like this. So part A of this example. From a group of 5 women and 7 men, so from a group of 5 women and 7 men. How many different groups or committees can be formed consisting of 2 women and 3 men? So how many different committees, think of groups, they're the same thing, can be formed consisting of 2 women and 3 men. So what does this group even look like? Well, you have a group of 5 people, and 2 of them are women and 3 of them should be men. And that's what the question is asking. How many different committees of those types of groups do we have? So how many different committees of 2 women and 3 men do we have? Well, we could extrapolate this to the permutation like we did here and so on. But again, it turns out doing this is much easier and faster and more intuitive, I think. So the first thing you should do is recognize, is this a combination problem or is it a permutation problem? Well, the question is asking how many different committees. Right there, I think of combinations. Don't even think of permutations, because it's not asking how many different arrangements can be made. It's asking how many different committees, how many different groups are there. So that's a combination problem. Okay, next thing you should do is recognize how many experiments you have and what are they. Well, I think we have 2 experiments here. Experiment number 1 is, well, I'm choosing 2 women from the 5 women, right? So that's my first experiment. Choosing 2 women from 5 women. Now let's just focus on this for now. You're choosing 2 women from the 5 women. Okay. Since it's a combination problem, we have to recognize what is our N and what is our R. What is our N? Well, just by going from the properties, N is always greater or equal to R. So if we're just focusing on women, right? We have 5 women or 2 women. 5 is greater than 2, so N must be 5. Also, the way you can think about it is you're choosing 2 women from 5. 5 choose 2. Okay, so that means R must be 2. So how many outcomes does experiment number 1 have? Well, N choose R. That's the number of outcomes, number of committees for the woman. So 5 choose 2 is the number of outcomes for experiment 1. Remember, this ends up being a number, right? 5 choose 2 is a number because this reduces to this, and this reduces to some number like that. Okay, great. We found the number of outcomes for our first experiment. What about our second experiment? Well, what is our second experiment? Well, our second experiment should be choosing 3 men from the 7 men, right? So choosing 3 men from the 7. And just like before, what is our n and what is our r in this case for experiment 2? Where, well, n must be 7, right? Because 7 is greater than 3. And then r is 3, well, because you're choosing r from the 7. So the number of outcomes for experiment 2 must be 7, choose 3. Great. We found out all of our experiments. We found the number of outcomes for each experiment. So by the basic principle of counting, so B, P, and C, we have a total of, by the basic principle of counting, says you have to multiply these two together. So you should have 5, choose 2 times 7, choose 3. And now you guys might see why I like this notation better. Because it already has the parentheses and it acts like its own sort of thing. When I have the other notation, it doesn't look as nice. So I like this much better, and you already see the multiplication here. And once you multiply that out, you just punch this in your calculator. If you have a scientific calculator, it already has the combination in it. So this ends up being 350 possible groups. 350 different groups or committees. And that's it. That ends part A, 350. So notice how these problems boil down to. You always have to find the number of experiments. You always have to find your n and your r, and then you have to find the number of outcomes for each experiment, and then end with the basic principle of counting, and then multiply the number of outcomes together. And you should get the total number of outcomes. Even when you're dealing with combinations or permutations, it ends the same way. And that's it, 350. Okay, so this brings us to part B, which can be a little tricky because there are a few ways to solve it. So I especially encourage you guys to try it out on your own, and I'm actually curious to see the way you solved it first, because there are 2 solutions to this, and I like one more than the other, and I'll tell you right after I finish the second solution which one I like more. So I'll erase this, erase the properties. Okay, that's that. And this is part B. And part B says, what if two men, let's say Mike and Bob, are feuding, so they're fighting with each other, and they refuse to serve on the committee together, and they refuse to serve on the committee together. And we still want to know the same, we still want to have the same question. How many different committees do we have? How many different groups do we have? Groups of 5, right? Because 2 women and 3 men. So how many different groups do we have? Well, so this is our first solution. Don't want to say anything before we dive in. No? Okay. Well, for the woman, we still should have the same number of outcomes, right? Because the women aren't feuding with each other. So the woman in experiment 1 still have a 5 choose 2 number of outcomes. So experiment 1, from there, we still have 5 choose 2 for women. Now, experiment 2 is, well, we're still choosing 3 men from the 7 men. But here's the problem. Mike and Bob do not want to be in the committee together. So any group of 3 men, right, because we're choosing 3 men from the 7, any group that has Mike and Bob is a bad group, right? Because Mike and Bob cannot be in the same group. They are fighting with each other. So we should have 2 cases for experiment 2. And this is it. So experiment 2 has 2 cases. So 2 cases. And this is important. Here's our first case. Case 1. Well, if they don't want to work together, then how about we don't even include both of them, right? Because if they don't want to work together, then let's not even include them in the 7 men to choose from. So because they don't want to work together, our first case is we can refuse to take both of the men. To take both Mike and Bob. Which means, well, if we refuse to even consider Mike and Bob from the 7 men, that means we subtract them off from the 7 men we even had to start with. So now, instead of 7 men to choose from, we have 5 men to choose from, right? Because I don't want Mike and Bob, right? I can't even have both of them in my group. So I'm not even going to consider them, right? This is the 2, that's where it's coming from, because there's 2 of them that are feuding. So yeah, before we had 7 men to choose from, but since they're feuding, I'm not even going to consider them. So now I have 5 men to choose from. So 5 men to choose from. Okay. So, okay, great. So we have 5 men to choose from. Now we still have to understand what is our N and what is our R. Okay, what is our N? Well, before we had 7. And that's because we had 7 men to choose from in the beginning. But I don't have 7 men anymore. I have 5 men, right? Because I'm disregarding Mike and Bob since they're feuding with each other. So then N is 5 now, because I only have 5 men to consider. Well, I'm still choosing 3 men from the new 5, so R is still 3, right? Because I'm still forming a group of 3 for the men. Oh, N and R, I have both of them, so the number of outcomes for case 1 in experiment 2 is 5 choose 3. And then we would be done, right? But we have 2 cases, and you'll see what the second case is now. So case 2. And remember, these are all within experiment 2, not experiment 1. Because we're only dealing with men here. That's where the problem is. Well, what can our second case be? We already covered the first, right? We don't even consider Mike and Bob. But since both of them are refuting, what if I just take one of them? Well, that's fair, right? I could choose one of them, because if I choose Mike and I don't choose Bob, well, then Mike won't be feuding with anyone else because Bob isn't in my group. Or what if I choose Bob and not Mike? That's fine also, right? Because Mike and Bob aren't together. And that's what we don't want. Since they're not together, that's fine. So the second case is, well, I could choose one of them. So we can just take one of them. One of the feuding men, right? We could take one of the feuding men. Okay, so what does this mean? If I'm just going to be considering one of the feuding men, well, if I don't consider Mike, then I should have 7 minus 1, which is 6 men to choose from now, instead of 5. Because now I'm considering only one of them and not refusing both of them. So I'm only considering one, and I'm removing one of them from consideration. So I'm just subtracting off one from the 7 men I had in the beginning. So now I have 6 men to choose from. Okay. So in case 2, what is our new n? Well, I have 6 total men now to choose from. So n equals 6. And what is our r? Well, we're still forming a group of 3 for the men. So r still equals 3. So the number of outcomes for case 2 in experiment 2 is n choose r or 6 choose 3. 6 choose 3. Great. Now what do we do? Okay, so experiment 1 we have this many outcomes. Experiment 2, it seems like we have 2 separate outcomes. Do we multiply these together? Do we subtract them? What do we do with them? Well, we have 2 different cases, so either one of them can happen. So we have to account for that. Well, if one of them can happen, either this or that, we have to add them together, which means we have to do case 1. So case 1 plus case 2, because either one of them can happen. Either we refuse to take both of them, or we can just take one of them. So we have to add them. So for experiment 2, the total number of outcomes is actually 5 choose 3 plus 6 choose 3. And we add them because one of them can happen, or the or, right? Either one. And this gives you the total number of outcomes for experiment 2. And we're basically almost there, right? We have the number of outcomes for experiment 2, and we have the number of outcomes for experiment 1, and by the basic principle of counting, we have to multiply these 2 together. Oh, sorry, these 2 together. And we're done. So, in total, where should I write this? So in total, we have 5 choose 2 for the woman, right? Because the women weren't a problem, times this sum, which is 5 choose 3 plus 6 choose 3. Right? This is the number of outcomes for experiment 1 when we chose women. And this sum is the number of outcomes for experiment 2 because we had 2 separate cases to deal with. So we add them, then we multiply them together by the basic principle of counting, and you end up with 300 possible groups. Notice how it's less than what we had before. And that should make sense, right? Because, well, 2 of the men are feuding. So case 1 says we don't take both of them, and case 2 says we only take one of them. So we're basically subtracting off the groups where Mike and Bob are together. And that brings us to our second solution of this problem. So you'll see we'll end up with the same number of possible groups in our second solution. And the second solution I think is a little more intuitive. If this worked for you, then that's great, but once you see solution 2, it might make more sense to some. So I'll be doing that over there. Okay, so solution 2. Okay. Okay, so this brings us to our second solution. So let's try that. So second solution for part B. And I guess, the biggest takeaway is there are many ways to solve counting problems, and that's why a lot of people struggle with chapter 1, because there are so many different ways to really count it. But you'll see once we get to probability, it doesn't get as bad, and you guys should really stick through this. It's not too, it's doable. You guys can do it. It's not too bad. Okay. So how do we approach our second solution? Well, this is how we start. So we know that for the men, 2 refuse to work together. So let's consider how many groups of 3 men contain the feuding men. Okay, so that's our first consideration. How many groups contain the feuding men? Contain the feuding men. That's our first sort of question when dealing with this problem. Well, how many groups contain the feuding men? How do we answer this question? Well, it seems like a combination question, right? Because how many groups? That's a combination. Okay. And we have one experiment. We're choosing what? We're choosing how many groups contain the feuding men? Well, let's see. What's experiment number 1? Right? It's always good to start with at least one experiment and see where it goes. So, experiment 1 is, well, how many ways can you choose Mike and Bob in general? What do I mean by that? Experiment 1 is choosing the 2 feuding men. Experiment 1 is choosing the 2 feuding men from what? Well, we have to choose Mike and Bob from themselves. Choosing the 2 feuding men from the 2 men that are feuding, right? That's experiment 1. You're choosing Mike and Bob from Mike and Bob. Because we want to know, first we have to choose the 2 feuding men, right? Before we even choose the men. So choosing the feuding men, you only could choose 2 of them from the 2. And, well, what is our N? And what is our R in this case? Notice, we have two of the same numbers. So it doesn't really matter. All you have to do is just write 2 and 2. But another way to think of it is you're choosing 2 from 2. So N choose R, 2 choose 2. So the number of outcomes for experiment 1 is 2 choose 2. And I'll just leave it like that for now. Now what was How do I even get experiment 1? Well, you have to think first. The question is asking how many groups contain the feuding men. Contain the feuding men. Well, I have to include the feuding men first, right? How many feuding men are there? There are 2. And I want to choose both of them to be in the group. So 2, choose 2. Experiment number 2. Choose the last man for the group. Out of the remaining men. I'm telling you guys, I really can't spell today. Remaining men. Okay, what does this mean? I have to choose the last man from the group, for the group, out of the remaining men. Why do I have to choose one man? Well, think about it. I already chose 2 to be my group. The question, if you have in your notes, said we have to choose 3 men to form a group. I already chose 2, so I have to choose 1 more to form my group of 3. How many remaining men do I have? I have 5, because I already chose 2. 7 minus 2 is 5. I have 5 men to choose from, but I only have to choose 1 more man. Oh, so I have to choose 1 man from 5 men. I have to choose 1 man from 5 men. I have an N, I have an R, so the total number of outcomes for the last man is 5, choose 1, right? Okay, so what do I have? I already chose my feuding men, and for my last spot, I already chose the last man. These are the only experiments I have. So I have to multiply these 2 together. So I have 2 choose 2 times 5 choose 1. Remember, 2 choose 2 is 1, right? Because it's n choose n. Like we had before with the properties, n choose n is n choose 0 is 1. So this is 1, so we have 5 choose 1. 5 choose 1 is 5. So this equals 5. What is this? This is the number of groups that contain both Mike and Bob. Groups that contain both Mike and Bob. Great. Why do we need to even find the number of groups that contain both Mike and Bob? Well, remember here, we don't want our group to contain Mike and Bob because they're feuding together. So this already covers the 2 cases. 5 groups contain both Mike and Bob. Okay, if 5 groups contain both of them, how many groups don't contain both of them? Meaning how many groups contain either one of them or none of them? Well, in the beginning, it's not here, but in the beginning, we had 7 men, and we had to choose 3 from the 7. So in the beginning, we had 7 choose 3 men. And that's the number of that's the number of total groups of men. But now, I have to subtract all the number of groups that contain both Mike and Bob. And the reason I'm subtracting them, this ends up being 35, and this is minus 5, so this is 30. The reason I'm subtracting them is because 30 is the number of groups that do not contain both of them. This accounts for the groups that may contain one of them and may contain none of them. And that's exactly what both of these cases do. This gives you 30. If you count 5 choose 3 plus 6 choose 3 is 30. So 30 different groups that do not contain both Mike and Bob. And this already finished for the men. The woman is still 5 choose 2. So in total, we have 30 times 5 choose 2. 30 times 5 choose 2. 5 choose 2, if you do it in your calculator, is 10. 30 times 10 is 300. Which is exactly that. So basically this 30 covers case 1 and case 2, but I think it's in a more intuitive way. Because first when you consider this question, how many of the groups even contain the feuding men? You find that out, right? 2 choose 2 times 5 choose 1 is the number of groups that contain both Mike and Bob. Then from the total number of groups of men, you subtract all of the groups that contain both of them, and you get the total number of groups that do not contain both of them. And then you multiply it by the number of ways you could pick the woman, and you get 300, which is exactly what we got here. And that's our second solution to the same problem. Which I like this better, but a lot of people like this more better. It really depends on how you think and how you're wired. But both of these are legitimate. It doesn't really matter which one you do. And I think they both take about the same time. But yeah, that's that. That's that. Okay. So this next question is actually our last question for combinations. And the reason it's our last question is because all these questions are kind of in depth. And once we get to the end of the chapter problems, we'll be doing a lot more combination problems. So don't fret. I just want to go into these deep problems just so you can get used to looking at the notation, working with multiplication, the basic principle of counting, working with maybe a more intuitive approach with combinations, and so on. Okay, so let's move on to our last example, and then after this example, I'm just going to give you guys one more sort of definition, and then we'll be done. Okay, I'll erase this. Okay. Alright. So, example. So, consider a set of n phones, so n total phones, of which m are broken, of which m of them are broken. Oops. So you have n phones of which m are broken. And n minus m are working. They're functional. Right? Because you should have n minus m that are working. If m are broken, right, n minus m are the rest of the phones which are working. And assume that all of the broken phones and actually all of the broken phones are indistinguishable from each other. And And same for the working phones. So the working phones are indistinguishable, meaning I cannot tell apart one working phone and the other working phone. I cannot tell apart one broken phone and another broken phone. And same for working phones. Same for working phones. And we want to know how many linear orderings, are there in which no two broken phones are consecutive? Consecutive. Question mark. No two broken phones are consecutive means you cannot have two broken phones together. There has to be at least one space between them. Okay. Well, this problem is kind of hard to approach with arbitrary number phones and broken phones and so on. So what I'd like to do is actually pick some numbers for n and m. So let's do a smaller example here. So let's let n equal 10. So this is the total number of phones in general. Let m equal 4, and this is the number of broken phones, right? That must mean n minus m of them. 10 minus 4, 6 of them are working. So they work. Number of working phones. Great. Well, we want to know how many linear orderings are there in which no two broken phones are consecutive. First of all, how do we know this is a combination problem? Well, this line says it right here. Assume that all of the broken phones and all of the working phones are indistinguishable from each other. So when I can't distinguish between one broken phone and another broken phone or a working phone with a working phone, that tells you it's a combination because since they're indistinguishable, order doesn't matter. And if you remember when we did permutations and there were objects that looked the same, we actually had to divide out by the number of ways we could rearrange those objects. This is exactly the same thing. So this line right here tells you that this is a combination problem. So whenever you see maybe indistinguishable, you can also think combination. Okay, so now we know it's a combination problem. The question is asking how many linear orderings. That means I'm aligning all these phones together and I want to know how many different groups of linear orderings are there. Well, let's first align the working phones together, okay? And we have 6 of them. So let's align them. So I'll represent a working phone like a big rectangle. So 1, 2, 3, 4, 5, 6. So these are the 6 working phones, right? So, okay. So 6 working phones. And they're aligned together. And we know that no two consecutive broken phones can be together. So I can't have 2 broken phones. I can't have, for example, 1 working phone and 2 broken phones like this. This is bad. We don't want this. So that means we need at least one working phone between them. Well, okay, let's put spaces between the working phones, and for each of those spaces we can see how many broken phones can fill them out, right? Okay, so we can have a space, so I'll represent this as a space over here, right? And then I have another space for a broken phone between these two, another space between these two, and so on. So let me just draw that out. So 1, 2, 3, 4, 5, another space, and then I can have a broken phone here as well. So these little, they're called carets, represent a space where I could put a broken phone, right? And this is a linear ordering. But now I have to understand, okay, wait, I have 7 spaces, right? 1, 2, 3, 4, 5, 6, 7. I have 7 spaces, and I could fill in any of them with the number of broken phones I have. Well, I only have 4 broken phones, but I have 7 spaces. So I have 7, choose 4. So I have 7, choose 4 different linear orderings, right? This is the linear ordering. I have to choose 4 broken phones from the 7 spaces I have between my working phones, and including this space and that space. So 7, choose 4 total linear orderings. And we're done for this example. 7, choose 4 linear orderings, right? Because I'm choosing 4 broken phones to fill out 4 of these spaces, but out of the 7 total spaces we have between each working phone and these 2. So 7, choose 4, and that's that. Now that we covered this little example, let's try to translate it to this general example. Well, we have n phones, m broken phones, and n minus m of them are working. Okay. So, notice that the 4 represents the number of broken phones, which is m. So I already know I should have an m as my r. The 7. Where do we get the 7 from? Well, the 7 is the number of spaces, right? The number of spaces that are here. 1, 2, 3, 4, 5, 6, 7. Notice we have 6 working phones. To get 7 spaces, you have to understand that you could have 1, 2, 3, 4, 5 spaces between each working phone, and then 2 spaces, 1 to the left of the first working phone, and 1 to the right of the last working phone. So that means we should have 6 plus 1. 6 working phones plus 1 will give you 7 total spaces. 6 is the number of working phones, so n minus m. But we have to account for maybe 1 more space here or here, plus 1, and you're done. That's it. That's the answer to this question. And whenever you have a question that has arbitrary variables, I really recommend you guys try to first bring it to a smaller problem with actual numbers, and then correctly translate it to this. So getting from here to here for the m is easy. From the 7 to this is a little tricky, right? Because you have to understand where's that 7 coming from. Well, you have 7 total spaces because you have 6 phones. You have 5 spaces between each phone, but you also can have 1 space here and another space here. 5 plus 2 of those spaces is 7. Oh, 6 working phones, that's n minus m. Plus 1 will give you the 7. N minus m plus 1. And that's it. That's your answer. That's how many different linear orderings are possible. And that's it. So that was our last example. And as you guys see, it may take a lot more work than solving the permutation problems, but honestly, I feel like it's more intuitive, and it's actually, it utilizes the experiments better in my opinion. And you'll see later you'll come to favor combinations, and we'll sort of forget about permutations later on. We'll still be using them, and we can still use them to solve the same type of problem, but you'll see later that using combinations is a lot easier, and it actually reduces the problem to a problem you'd like to solve. So we're done with all the problems for this video, and I just want to leave you guys with one more definition, and then we'll be done. So let me erase everything and we'll get to it. It's just a identity that may be useful. Okay. All right. So, a useful combinatorial identity. Combinatorial identity. And this identity is called Pascal's rule. Okay? Pascal's rule. And this is what he came up with. He found another way to represent n choose r. And this is how it looks. So n choose r equals n minus 1 choose r minus 1 plus n minus 1 choose r. And this is only true when r is between 1 and n. It's not true when r equals 0. So this has to hold for this to be true. But this is what Pascal found, that n choose r can be separated into a sum of these two combinations. And we're not going to prove that is true, but it is. But I will give you guys a sort of intuitive way to look at it, because I think it helps to sort of see, how can this be useful. So here's what I want you to consider. Consider n balls in the basket. So consider n balls, n balls in a basket. So you have like a basket, right? Oh my god. I'm not an artist, so this might look really bad if I can't draw a basket. Oh god, okay. I'm just gonna go for it. Here's your basket, and you have a total of n balls in it. Okay. Oh god, that's just sad that I can't draw a basket. Like, then you should have, no. Like that, I guess, right? You have n balls in there. Out of the n balls that you have, one of them is red. Okay, so out of the n that you have, one is red. Okay, so you have one red ball, and the rest are green. Are green. So that means, well, you have n balls. one of them is red and the rest are green. So how many green balls do we have? Well, we should have n minus the red because the rest are green. So n minus 1. That's the number of green balls that you have. Okay, so this is what we want to consider. One way of choosing a certain number of balls from the n that you have is n choose that number, right? Or n choose r. So one way of choosing, one way of choosing r balls from n is n choose r, right? And that gives us the left hand, right? We already know this. We've been doing problems using that. So that's one way of choosing r balls from n. And now we're going to see how we can get this. So the other way is to see when you choose the R balls if we have the red ball or we don't. Is to see when we choose, oh my god. When we choose the R from the N. How many of the R is a red ball and how many isn't? So not how many. Do we have the red ball or do we not? So if we have the red ball, or not. Okay. So this way we already covered, right? And choose R. Now this next question is considering, well, when we choose the R balls from the N, when do we have the red ball and when do we not have the red ball? So that's two cases, right? So we have two cases, and case one, let's have it say we have the red ball. Okay, we have the red ball. Okay. So we want the red ball to be in the R balls we choose from the N. We have the red ball. Well, that means, what does that mean? That means from the basket that has N balls. So the basket that has N balls, we're taking out the red ball, right? We want the red ball to be in our collection. Well, then we have N minus 1 left in the basket, right? So we have N minus 1 left once we have taken out the red ball. Well, how many ways can we choose the red ball so we have it in our group? Well, we only have one red ball and we can only choose it in one way. So 1 choose 1. This is the number of outcomes for our first experiment. And our first experiment is you want to choose the red ball from your red ball. You have one red ball to choose from the one you already have. And now your second experiment is choosing the rest of the balls. Well, the rest of the balls, so how many total balls do you have left? You have N minus 1, which is the green balls. right? You have n minus 1 left because you took out the red ball. Oh, but we have to still choose the r. Well, we already chose 1, so we don't have r now. We have r minus 1. So we have r minus 1. And what this gives you is for case 2. We have the red ball. So this is the group that contains the red ball. Okay. Case 2 is we pick no red balls from the R. We pick 0 red balls from R. So we don't even want to consider the red ball anymore, right? So instead of having n total balls, if we don't consider the red ball at all, we have to subtract that ball off. So now we have n minus 1 total balls to choose from. But we still want to choose R. We still want to choose R from the remaining balls. Right? We still want to choose R. So we have n minus 1 choose R. Different groups that contain 0 red balls. Because we already subtracted off that red ball. I threw it away. It's not even, we're not considering it. But we still want to choose R. So, case 1 and case 2, you have 2 different cases. Either one of them can happen. So you have to add them together. So case 1 plus case 2 is, well, 1 choose 1 is, remember n choose n always gives you 1. 1 choose 1 is just 1. 1 times this is n minus 1 choose r minus 1. And then we have to add this because they're 2 separate cases. N minus 1 choose r. And that's the total number of outcomes for when we have the red ball and when we don't have the red ball. Oh, but this accounts for that. This already accounts for the groups that do contain the red ball and the groups that do not contain the red ball. So in fact, this does equal n choose r. And that's one way of seeing how Pascal's identity is true. Of course, this is not a proof, but it's just a way of seeing where this make come from. And that's that. So I'll end this lesson with this identity. And then in the next lesson, we'll be finishing up combinatorial analysis. So we'll be looking at the binomial theorem, multinomial coefficients. I'll tell you guys what that is in the next video. And the number of integer solutions to equations and how we could use the binomial theorem and combinations to actually find out how many solutions your equation has, which is a little interesting. But this is the end of this video. I hope you guys enjoyed it. If you like the content that I'm presenting, please make sure to like and subscribe. And especially if you subscribe, you won't miss out on any content. So I highly advise you guys to do so. If you guys weren't sure of anything I did in this video, please leave down a comment and I'll try to get back to you. As always, have a great day and bye.